All right, well, I will begin with the word of prayer. Dear Father, we thank you for this day again. I thank you for this class and the break. And just pray that you'd be with us this morning and help us to glorify what we do and just understand a little bit more about your creation together, Lord. You know my prayer, Lord Jesus. Amen. So you guys have a good break? Yes, no? Yes. Mine was pretty good, although my most fanatical swimming son, Isaac, he's come down with the flu, I think, so it's not awesome. But it's like yesterday, he's starting to feel bad, and then this morning my wife's like, he's got 103 fever. I'm like, oh, yay. So anyway, so that's fun. So I wanted to talk about, we talked before, right before break about diagonalization. So I should talk about that again a little bit. And so like here's basically the definition given a, right, say an n by n real matrix. It could be complex, but I'll keep it real here for a second. If there exists P invertible such that P inverse AP is equal to a diagonal matrix, so that would look something like, right? And I mentioned we could also write that as like D1, E1, Dn, En, right? So that's what it means for a matrix to be diagonalizable, is that we can find a similarity transformation which takes the matrix from the form that it has to this super special, nice, mostly zero but non-zero entries down the diagonal form, right? In this context, a lot of times people use like a big D for diagonal in this context, all right? Now the theorem I proved before break, if you missed it, and a lot of you guys were here, but some of you weren't, and this is the theorem, is simply this. I guess I need to finish my sentence here. Given A, there exists P, then A is diagonalizable. And this is the theorem. A is diagonalizable if and only if there exists an eigenbasis for A, right? Moreover, if there exists, say, V1, V2, Vn, linearly independent vectors in Rn with eigenvalues lambda 1, lambda 2, lambda n respective. And if we say P is the matrix you get from gluing these vectors together, then in that context, P inverse AP, we worked it out. It's actually a diagonal matrix where you've got the eigenvalues down the diagonal. All right. So this is a pretty important result for this class that we need to make sure we understand and are able to implement and use. I showed last class that we can actually put this into practice. We actually took a matrix, we found an eigenbasis. An eigenbasis is simply a set of n vectors which are linearly independent. And I guess I've missed an important equation here. which is what? I need to tell you that these vectors are eigenvectors. So missing a such that A Vj equals to lambda j Vj, right? For all j, 1 through n. So you have, if you can find n linearly independent eigenvectors with eigenvalues lambda 1 through lambda n respective, that could be repeated in my current formalism, all right? Then the matrix is diagonalizable, and in particular, this is its form, right? Any questions before I say more? So last class, like before break, I actually looked at an example, and we did this. We actually found the matrix of eigenvectors, and we did the similarity. This is called a similarity transformation, right here. A similarity transformation is something you can do to a matrix, right, to change to another matrix. Remember, the significance of this is that if we have a linear transformation T from Rn to Rn, right, then the matrix with respect to the beta basis was equal to the basis matrix inverse times the standard matrix of T times the basis matrix, right? So you can think of this as P inverse standard matrix of P. So a similarity transformation corresponds to a change of coordinates, right, for a linear transformation. And so another way of looking at this result is that if you have a linear transformation and its standard matrix is diagonalizable, then that means that there's a formula in eigencoordinates which makes the linear transformation especially simple, right? All right. So the other thing I mentioned is that there are all kinds of, once you have a diagonalization for the matrix, there's a couple different intellectual directions we can go at this point, right? The one direction we can go is to start asking some soul-searching questions about when is it possible to diagonalize a matrix, right? That's one direction we need to explore. A different direction to explore is, okay, so if it's diagonalizable, what new exciting calculations does that make possible, right? So we'll explore both of those directions. I'll start with question number 2. One of the things I pointed out, it was just kind of a passing comment at the end, but if we have D as P inverse AP, notice that we then also have that P D P inverse is P inverse a P inverse, right? If I multiply on the left by P and on the right by P inverse, I have that. And how's that simplify? What does that do for you? We can cancel out the P and P inverse, right? What's that give us? Yeah, we get A is equal to, apparently, P D P inverse. Notice that the position of the P and P inverse is different than it was before, right? What's the formula for A squared? Well, it's A times A, right? Which is also P D P inverse times P D P inverse. Look at that. Notice that the middle copy of P inverse and P, they'd be canceling, right? That gives you the identity matrix. And then you just have what? D times D, right? A D squared. See that? A D squared. So I'm just left with P D squared P inverse, right? What if I had A cubed? A, right? I end up with P d cubed P inverse. See that? Because the same calculation will go with 2 copies of P inverse and P in the middle, squashing to the identity, right? And generally speaking, a to the power n is going to be P d to the power n P inverse. This right here is a nice formula to calculate a to the n, since d to the n is easy. What's d to the n? If I have lambda 1, a lambda 2, lambda n, and I raise it to the n power, what do I get? Let's forget about n power. Let's put the k power here for the sake of discussion. What I end up with is lambda 1 to the k, lambda 2 to the k, lambda n to the power k. So like a diagonal matrix is simply the diagonal matrix exponentiated is simply the matrix of the diagonals exponentiated, which is much easier than multiplying a matrix n times, right? I mean, like, goodness gracious, like way easier, right? Now, let's see here. The other application, so that's one application of diagonalization. Another application is differential equations. So if we have that, let's see here, P inverse, my bad, beta inverse, A beta, right, is equal to this diagonal matrix like that. And if we, let's say, let y equal to beta inverse times x. So this is AKA the beta coordinate of x is equal to y. In this context, what I'm talking about, I would say y is an eigencoordinate. Y is a system of eigencoordinates for this matrix. Y is a system of eigencoordinates. So we were trying to solve sometimes, as our principal application to all this stuff, the system of differential equations, what, dx dt is equal to ax. I guess I don't think I put, did I put vectors in here? I can't remember, guys. We could put a vector over x if it makes you feel better about it. You don't have to if you don't want to. If you're in physics, I'll take points off if you don't. Anyway, so if you want to adorn this with an x, you're welcome to, but you don't have to if you don't want to. I'm gonna opt not to here, if you guys don't mind. Okay, because the context makes it clear that it's a vector in here. All right, so how can I replace this x with a y? This right here, guys. What's x equal to? X is equal to what? I multiply both sides of that equation on the left-hand side by the beta matrix, right? And that will cancel with beta inverse, and I get beta y, right? Multiply this by the beta matrix on the left, I get beta y is equal to beta times beta inverse times x. Beta inverse cancel, just leave me x. Flip it. So that's what x is in terms of y. Plug that in down here, what do we get? We get d dt of the basis matrix times y is equal to a times the basis matrix times y, right? Making that substitution. Now, is there any time dependence to the basis? There is no time dependence to the basis, right? So I can pull the basis out of the derivative here, like this, by the rules of calculus we talked about. Started last week. Like that. All right. And then I can multiply by the inverse of the beta matrix on both sides, and this gives me what? This gives me that dy dt is equal to the basis matrix inverse times A times beta times Y. But remember what the similarity transformation of A by the basis matrix is. It's the diagonal matrix, right? So this is lambda 1 through lambda n times my y, which I'll enumerate y1 through yn, right? And if you just look at this, what we have is that dyj dt is equal to lambda j times yj for all j. Which is super nice because if you've had calculus 2, and I'm told you have, you've already solved this differential equation. Should have been like the first or second one you did when you're talking about separation of variables. Separate, integrate, clean it up. The solution's an exponential, right? So this has solution yj is equal to like a constant times e to the lambda j t by calculus 2. And yeah, so so we get, in summary, we get y is equal to like c1 well, let's see here. Fine, yeah, c1 e to the lambda 1t cn e to the lambda nt, right? And then what was x? X was equal to what? X was equal to beta times y, right? Which is going back v1, v2, vn times my y, which is apparently c e to the lambda 1, cn e to the lambda nt. And lo and behold, what we got? We have c1 e to the lambda 1t times v1, c2 e to the lambda 2t times v2, plus cn e to the lambda nt times vn. And there you go, that's the general solution to the differential equation. This is not how I did it last week, right? Like last week, well, first of all, last week we were all relaxing, I guess, or doing something. This is not the way I did it last week, right? Or last class week, I should say, was to just write down these solutions, For a problem, I just said, okay, we'll find the eigenvectors, find the eigenvalues. I told you that this is a result. We can build the solution like that, right? Now I'm showing you that if the matrix is diagonalizable, I can literally change coordinates, do calculus 2 on the problem, and then write down the solution just using this. Which, of course, gets us back to where I guessed at the start of everything, which was that we can construct our solution using eigensolutions. All right. So that's an important application for us. Let's see if I can find you guys a problem here. Suppose we have A equal to, let me just make something up here, 3, 1, 1, 3. I don't think I've done this one yet. Let's see if we can diagonalize this matrix, all right? So what do? We calculate the characteristic equation. I get lambda minus 3 quantity squared minus 1, also known as lambda minus 3 plus 1 times lambda minus 3 minus 1, which apparently gives me lambda minus a 2 times lambda minus a 4. Lambda 1 is 2, lambda 2 is 4. If I've already done this example in this class, my apologies. I really did try to review what we did before break, before class. This feels like I've done this example already this semester. I'm not sure which class I did it in, though. Anyway, it's good for us to go through again. Okay, good. Yeah, all right, very good. So let's find the eigenvalues. If you don't mind, I'm going to do the eigenvalues up above. I guess I'm doing it here. All right, so I'm talking about a minus 2I times u1. This is my lambda 1 equals to 2 problem. So what I'm looking at then is 1, 1, 1, 1 times u1 equals to 0. That's my problem for that one. Lambda 2 equals to 4. I've got to solve a minus 4I times u2, which is minus 1, 1, 1, minus 1 times u2 equals to 0, 0, right? And so, if you look at this, this tells me that u1 is basically anything u times the vector, let's say, 1 minus 1. And this tells me that u2 is anything u times the vector 1, 1 will do. If we solve those equations, right? You can check that what I wrote down is legitimate, right? As long as u is what? There is one choice we cannot make. Eigenvectors must be non-zero. If I make u equal to 0, we're in trouble, right? So let's not do that. As long as we don't do that, we have non-zero vectors. Now, did you notice something about these vectors? They're what? Take the dot product of u1 and u2, what do you get? What's the angle between these vectors? 90 degrees, right? The dot product of u1 and u2 is 0. That means these are orthogonal vectors. If we normalize them, we'll have an orthonormal set of vectors. So if we use u1, 1 over the square root of 2, 1 minus 1, and if we use u2, 1 over the square root of 2, 1, 1, that'd be super nice. Then that would make these orthonormal, which means the perpendicular and length 1. We talked about this a little bit before, but just to emphasize again, orthonormal bases are the nicest ones, because in this context, if I make my basis matrix beta like u1, u2 like this, then the transpose, well, the inverse of the matrix is the transpose as it happens. All right. So let's see here. Let me just do it up here. All right, so in this context, if we look at basis matrix inverse times A times the basis matrix, my claim is that that's just basis matrix transpose. Now, all right, so like this we can write as 1 over the square root of 2 times 1 minus 1, 1, 1. And beta transpose we can write as what? 1 over the square root of 2 times 1 minus 1, 1, 1. Might as well pull the square root of 2 out, like the 1 over the square root of 2 out. Pull it out, why? Because it gives me no joy to write 1 over the square root of 2 8 times. Instead of writing it 8 times, I just wrote it 2 times. Okay, it's not coffee grounds, it's just raw sugar. It's better. These are very different. Very different. And coffee grounds still better than what it could be, you know, if you think about it. Okay, so if I think about this product right here, I've got a 1 over the square root of 2, and I've got another 1 over the square root of 2, right? So if I factor both of those out front, I get a half. So let's do that. I've got a 1/2. My basis inverse matrix is 1, minus 1, 1, 1. My matrix A was 3, 1, 1, 3. And then my basis matrix beta, 1, 1, minus 1, 1, right? So let's multiply that all out. What do we got here? 1 minus 1, 1, 1, and I'll do these guys. I get 4 minus 1 is 2. I get 1 minus 3 is minus 2. I get 3 plus 1 is 4. I get 4 again. So I get 2 minus 2 for the first column, 4, 4 for the second column. And then I get 1/2, multiply these matrices, what do I get? 2, 2 plus 2 is 4. And then I get 0 down here. I get 0 up here. And I get 4 plus 4, also known as 8. Bring the 2 in, what do we got? 4 over 2 is 2. 0, 0. 8 over 2 is 4. Not an accident, right, guys? Because that's lambda 1, 0, 0, lambda 2, as we should hope, right? This is what I said would happen, and it happened, right? Now that we've done this, let's calculate the nth power of this matrix. We can do that without like that much work, right? I guess as long as I've got this thing right above, I might as well point out if you were going to solve dx dt equal to like 3x plus y, right? And dy dt is equal to x plus 3y, right? Maybe I should use 1 and 2 here. I'll use 1 and 2, x1, x2, x1, x2. I'm changing it so the notation comports with what we were doing. All right, there. Then my solution is like x is c1 e to the 2t. And I can do like my u1 vector, c2 e to the 4t, my u2 vector. What did I not do here, guys? You didn't bring up 1 over root 2. That's right. So you could say I absorbed 1 over root 2 into the c1 and c2 if you like. Or if you'd rather, you could say I used the eigenbasis v1 and v2, which are just square root of 2 times my u1 and u2, all right? I don't need to write the square root of 2 in the solution there if I don't want to, right? It was important. It was important for the purpose of the 1 over root 2 is needed for this to happen here, all right? If I hadn't normalized the vectors, I would have actually had to calculate the inverse, like we did last class. Last class example we looked at, we actually had to calculate the inverse through a matrix calculation. It was kind of a pain. That generally happens unless you've got an orthonormal basis, which is super nice. All right, so now we've done that. What's the nth power of A? If I can find oh, here it is. I'll do it up here. So this was one application of this calculation. Obviously, we didn't need to actually do everything I did there in order to do what's up in the upper right-hand corner, right? We could have easily gone straight from where? Like once I get here, I can immediately write down the solution, right? I don't have to do this calculation here to do that, right? A to the power n, we can get from what? We can get from p d to the n p inverse, which in this case is, like I'll factor out the half again, yeah? So I've got p was my basis matrix, which was 1 minus 1 for the first column, 1, 1 for the second column. D to the n is what? What is d to the n? We're talking about 2, 4, right? To the nth power, right? But if you guys allow me to not write it again, let me just put the n where it belongs, which is in here, like that, right? And these are zeros. So that right there is really nice, because even calculating a cubed is a pain if we do it directly, right? But here we can calculate the nth power just like this. So 1/2. All right, so this gives me a 2 to the n, 4 to the n, minus 2 to the n, and 4 to the n. Then multiplying it, I get 1/2. I've got 2 to the power n plus 4 to the power n. I'll put some dividers in here for us. And then minus 2 to the n plus 4 to the n. And then minus 2 to the n plus 4 to the n. And then finally, make sure I did that right, just a second here. Oh, hold on a second. Was that, you guys tell me, is that last? Yeah, last step's okay. All right, so next, I got minus times minus is plus. So finally got it 2 to the n and plus 4 to the n, right? Right. Now we could bring the half inside the expression, or we could just leave it like that. I think I'm inclined to leave it like that, because I've got other things to do today besides this example. But there you go. That's a formula for a to the power n, right? Which you could easily check. Like try putting in n equals to 1, for example. Well, how about it? Does it work for n equals to 0? I wonder. Let's try it out. I wasn't even thinking about that, but how's that go? What's to the 0 power? What'd you get? 2? Yeah. Minus 1 plus 1, 0. Minus 1 plus 1, 0. 1 plus 1, 2. Okay, so yeah, 1, 0, 0, 1. That's a good sign. A to the 0 power should be an identity matrix. Yay. How about n equals to 1? Two plus 4, minus 2 plus 4, minus 2 plus 4, and 2 plus 4, also known as 1/2 of 6, 2, 2, 6, also known as 3, 1, 1, 3. Okay, good. Okay, that was what it's supposed to be, right? So my formula checks in 2 cases, therefore it must be true in all cases, right? Okay, that's not really true, but I guess if your boss is dumb enough, he might believe you. I don't know. Odds of you having a boss dumber than you are pretty high. You don't tell them that, though. Make them think your idea is their idea. That way they'll do it. For the record, I'm not talking about my boss. My boss is very smart. Let's see here. Where was I? Okay, so let us move on. So these are 2 nice applications of diagonalization. One is, of course, we can calculate the nth power of a thing. The other is we can solve a differential equation. All right. Not every matrix is diagonalizable, right? So let us feel the pain, so to speak, of what can make us fail to be diagonalized. We've seen this already last week of classes, right? We ran into a matrix which didn't have enough eigenvectors, right? If we don't have n linearly independent eigenvectors, we can't diagonalize. Do you guys know any nice conditions for linear independence of eigenvectors? I mean, if you've read the book or my notes, you might know. I don't think I've really told you in class yet. What was it? Oh, okay. So, so here's a theorem. if lambda 1, lambda 2, lambda k are distinct eigenvalues with eigenvectors v1, v2, vk, then these guys is linearly independent. So eigenvectors with distinct eigenvalues are linearly independent. That's one thing that's very nice. So like, for example, if you have n distinct eigenvalues for your n by n matrix, then it's diagonalizable. Because if you have n eigenvalues, they're distinct for n by n matrix. That means you have n linearly independent eigenvectors. Then you got an eigenbasis. So that's one nice thing. Generally speaking, another sort of result in this direction is that the geometric, so I'll say it in words. 1 is less than or equal to the geometric multiplicity of lambda j, which is less than or equal to the algebraic multiplicity of lambda j. The geometric multiplicity, we can write explicitly, this is the dimension of the null space of A minus lambda ji. All right. This, on the other hand, is the number of times lambda j appears as a solution for the determinant of A minus lambda I equals to 0. These are separate ideas, all right? In other words, the geometric multiplicity is the maximum number of linearly independent eigenvectors, whereas the algebraic multiplicity is simply the number of times that eigenvalue appears as a solution to the characteristic equation. This, at the bottom, tells you always have at least one eigenvector for each eigenvalue. But this inequality up here, it warns you might not always have enough. All right. In step 3 here, which is kind of a souped up version of number 1, let's, well, I'll just write it this way. If the geometric multiplicity of lambda j is equal to the algebraic multiplicity of lambda j for each lambda j in the reals, then A is diagonalizable. So what that means is if the algebraic multiplicity is equal to the geometric multiplicity and all your eigenvalues are real, that's another way of me telling you you have enough eigenvectors. This data in number 3 says that if we've got a 4 by 4 matrix, we've actually got 4 linearly independent eigenvectors. We got an eigenbasis. So number 3 is really equivalent to saying that there exists an eigenbasis for A, all right? But you notice this business right here. I just said for all of the eigenvalues being real, which means that we don't have to have real eigenvalues, right? So what else could happen? What is this? If we think about, the characteristic equation, what is it? What are we looking at? What is this for an n by n matrix? This is a what? This is an nth order polynomial equation with what? Real coefficients for an n by n matrix. But we know the fundamental theorem of algebra says such an equation has n solutions, possibly repeated, possibly complex. Now, because the polynomial that we're looking at has real coefficients, it follows that the complex solutions have to come in conjugate pairs. So all is not lost. And I think I've already showed you guys an example of this in the notes I projected, but we should work one out. Actually, we should work a few out. I'll work one today. I'll probably work another next class. What do we do when the eigenvalues are complex, right? So example 2 will illustrate that. So here we go. If we look at A equal to, we'll do 2 by 2 to start with here. Minus 2, 8, minus 10, 6. All right. Let's calculate the characteristic equation, see what the characteristic values are. So I've got myself determinant of A minus lambda I. This is my characteristic equation. I've got minus 2 minus a lambda, 8 minus 10, 6 minus lambda. Do the math here. We got lambda plus 2 times lambda minus 6 plus, 80. So if I multiply that all out, I've got myself a lambda squared. Plus 2 minus 6 is minus 4 lambda. And then I've got a minus 12 plus 80, 68, plus 68, all right? Complete the square. This is lambda minus 2 quantity squared. And I subtract 4, so I'm doing plus 64 after I complete this square. All right? So once I get to that form, I already know from the theory of polynomial algebra that lambda is 2 plus or minus 8i. All right? I do not need to look at the quadratic equation. Why would I do that when there's no need, complete the square. You can read off the solution right from there. All right? So I have, when I have lambda minus 2 plus 64 equal to 0, that means that my solutions are 2 plus or minus 8i. Do you guys want me to explain more? I could explain more. Sidebar. So if I have lambda minus 2 squared equals to minus 64, that means lambda minus 2 is equal to plus or minus the square root of minus 64, which is also known as plus or minus 8 times I. And therefore, I get, these are my two solutions, right? Great. So I want to look at, I'll choose the plus solution, right? And so I need to look at A minus parentheses 2 plus 8i times the identity matrix. All of that times my u vector equal to 0. That's the equation I'm trying to deal with. So I'll write this out. We've got minus 2, 8, minus 10, 6, minus the diagonal matrix where we've got a 2 plus 8i on the diagonals, and zeros elsewhere. Right? Now what happens is the 2 and the minus 2 cancel, and it leaves us the 8i. And then in the other one, it doesn't cancel. Some unpleasantness occurs. Let's see here. So we get minus 8i, and then 8. And then downstairs we get minus 10. Oh, we just did minus 10. Okay, it's fine, it's fine. And then 6 minus 2 is 4. 4 minus 8i down here. All right. All right. Yeah. Uh-oh.
Is the first one, is it negative 4 minus 8i? Negative 2 minus 2?
I really wanted those to cancel. But yeah, thank you. Well, thank you. I would have gotten very, very confused in about, well, a minute or two, I guess. Thank you. All right. So if we've done everything correctly, then these should be the same equation. So we can pick either one of them to solve. Which one do you guys want me to solve? Let us use, we'll use the top equation. Why not? All right. So this gives me minus 4 plus 8i times u plus 8v equals to 0. That suggests to me that v is equal to 4 minus 8i times u divided by 8, right? Which I can simplify a little bit. We can afford to do that much. This is 1 minus 2i times u divided by 2, right? If I cancel out the 4's. And so I suggest that we make u equals to 2, and that will give me u1 equal to, which we could just call u, I suppose, 2, and then 1 minus 2i. All right? Notice that if we have, here's like a general calculation, guys. If a is real, and if I have a times u vector is equal to, say, alpha plus I beta times u. So I'm saying I have a complex eigenvalue with real part alpha and imaginary part beta. If I take the complex conjugate of that equation, what this tells me is that a times u conjugate is equal to alpha minus I beta times u conjugate. The reason, like the complex conjugate of a is just a again, so we don't get an a conjugate. What I'm trying to tell you is that this has lambda equals to 2 plus 8i by our construction, right? If we wanted to, we could write down u2 is 2, 1 plus 2i, like this. That will have lambda conjugate, which in this case is 2 minus 8i as its eigenvalue. By the way, those are distinct eigenvalues, right? 2 plus 8i and 2 minus 8i, these are distinct, which goes to show you that my eigenvectors u1 and u2 are in fact linearly independent. And we can do more here, just to complete the thought. I'm going to erase this up here. We can do a little bit more. If we let P equal to the matrix, say U1, U2 like that, right? And if I was to calculate P inverse AP, what would I get? You're like, well, we've never inverted a 2 by 2 complex matrix. You can do it. It's the same thing. That formula we have, A, B, C, D inverse is 1 over AD minus BC. Flip the diagonals, put minuses on the off diagonal. That formula still works for complex 2 by 2 matrices. You can do it. And if you were to do that for this matrix, what you get is a diagonal matrix which has the form 2 plus 8i, 0, 0, 2 minus 8i. So this means that A is quote-unquote complex diagonalizable. But we wouldn't say that it's diagonalizable if we're keeping it real, because we can't diagonalize it using real mathematics. We have to resort to complex eigenvectors in order to diagonalize the matrix. And next time, I'll show you what this means for differential equations. This means if we look at the differential equation that corresponds to this matrix, we end up getting like sines and cosines in our solution is what ends up happening. But we don't have time to do that today, so we'll leave it for next time. Thanks, guys.